hopefully, at least I will definitely give you many results, but I'm not sure if I will have time to give details of constructions or proofs. We'll see. So first, let us set some notation. We will work with a simple algebraic G. We pick a pair of opposite Borel subgroups and corresponding unipotent subgroups. The intersection of positive and negative Borel, or our preferred pair of Borels, is a maximal torus. We'll also use a Dynkin diagram of our group, the corresponding while group, generated by simple reflections corresponding to vertices of the Dynkin diagram. Since we work with simple algebraic group, there exists a longest element, which we denote by W naught. One has a corresponding braid group, which is generated by sigma i's corresponding to si's, with the same relations with the same relations of the form sigma I plus 1, sigma I equals sigma I plus 1. Well, better write it more generally. Sorry. Sigma I, sigma j, sigma I is equal to sigma j, sigma I, sigma j if there is a edge between I and j, and they commute otherwise. I think most of you know this relation, so I will not write it in detail. The only difference with the while group is that they don't have to be square. We don't have sigma square equal to identity. It's just something. It's generated by, and this generated braid group. So in type A, if G is, for example, SLN, we get the usual braid group. With this, we can associate a flag variety, which again, just the usual flag variety in type A for SLN or GLN, which can be defined as G mod B, and various Borel subgroups can be identified with points in G mod B. In particular, the standard flag corresponds precisely to our preferred positive Borel. And for each word in positive braid submonoid, so something which is which is a product of sigma i's but not the inverses, we can define what's called Demeter product, which can be interpreted as, which can be defined recursively, but can also be described as the largest element of the while group with respect to Brouwer, such that beta contains its minimal lift of its reduced expression. For example, if you have a word sigma 1, sigma 1, sigma 2, then delta, oh, sorry. Then it's delta by is equal to sigma 1, sigma 2, or more precisely, S1, S2. So when we stutter, when we repeat some letter, it does not contribute to Demeter product, and when we get something which kind of should be larger when we take a projection to the while group, then we add such a letter. So when we have flags, we can describe the relative positions which correspond to elements in the while group, or in particular letters in the while group. So generally simple reflections. We have a Brouwer decomposition of the group, and we say that a pair of flags is in a relative position corresponding to an element of the while group if X inverse Y belongs to this Brouwer cell. So Brouwer cells are indexed by elements of the while group, say permutations in type A, and we have a well-defined notion of relative position, which in type A corresponds to saying that if you take two full flags, then they differ precisely at letters. So for simple reflection, they differ precisely in the vector space of dimension corresponding to this letter. And then you can take a product corresponding to reduced expression of W and say what it means. And this is the description which does not use vector spaces or anything. Now we can define a braid variety, which has appeared under different names in literature. So something similar is called brick variety, more on that later. Something very similar was called open Bode-Samuelson varieties. What is it? It is a moduli space of flags. So a bunch of flags in certain relative positions. It's one of the descriptions is given by this chain of flags, such that the first flag is taken to be standard. The last flag differs by de Mazur product of our word, and neighbors are in relative positions corresponding to the corresponding simple reflection. There are several properties. Such varieties are always smooth, irreducible, and of what one could say an expected dimension. So, for example, if beta is a reduced word, then it's just a point. If it's non-reduced, then we get something of a larger dimension. And the variety does not depend on the choice of a word, only on the element in the braid group. In fact. But for each word, there exists a certain compactification by so-called brick variety, which is due to Escobar. With the complement being a normal crossing divisor, and adjacency of the strata can be described by some cool combinatorial thing, which is called subword complex, or more precisely dual subword complex, which was defined by Allen Knudsen and Ezra Miller. And also the ring of regular functions, also sometimes called coordinate ring, is a unique factorization domain. So these are some nice varieties, and I will give some special case. I will list a couple of examples later, but just continue to discuss them a bit abstractly. What happens if we kind of change the word a little bit? We add a letter at the beginning or at the end. Then it depends on whether the de Mazur product changes or not, whether we get a larger maximal element, maximal permutation with some reduced expression being a subword of beta sigma I. Yeah. If the de Mazur product does increase, then we get the same variety. If it does not, then one can describe explicitly the subvariety, which is locally closed subvariety, isomorphic to inside the braid variety for a larger word, which is isomorphic to braid variety for a smaller one. But in general, we can assume that the de Mazur product is W naught because we can increase if we have de Mazur product shorter, we add reduced expression for a complement at the end. We get de Mazur product being W naught, and so very good. Hopefully that was not too fast. There is an alternative definition, which is roughly speaking described as guys as an affine algebraic variety. This is very natural description as an affine algebraic variety in type A and something slightly more complicated in other types. So we can define certain morphism from SL2 to our group a bunch of morphism, one for each simple root, or one for each vertex of the Dynkin diagram, where generators come. So one guy comes to upper triangular matrix, another to lower triangular matrix, and of course Cartan generator comes to something in the torus, essentially in the core root, corresponding to this vertex of the Dynkin diagram. Now we can define what one could call braid matrices, but it's really matrices, proper matrices only in type A, but let's call them braid matrices. By this condition, so in type A, you can forget about this phi I. You get this 2 by 2 block inside a huge matrix, n by n, where n is the number of vertices in the Dynkin diagram, number of generators, simple reflections, which has 1 on the diagonal, then which has this block 2 by 2, and then 1 again, and 0 everywhere else. So it has Z. Well, I won't write anything because it will be unreadable, but you get the gist. So this is in type A. And one can check that there is an alternative description of this flag configuration problem, flag incidence problem, which is given by this. So the permutation matrix for inverse of the de Mazur product, some permutation matrix, times these matrices is inside a Borel, so it's upper triangular if we are thinking in type A terms. Basically, a product of certain matrices with zi's being some entries is upper triangular, and clearly this is some condition on matrix entries in the product, so all the entries in the product below the diagonal have to vanish, and this gives a system of equations on zi's. So one can check that it's defined in a fine algebraic variety. And the various names and slightly different versions of these guys appeared in various situations. So such matrices, again in type A, or some variations of this which give isomorphic varieties, appears in studies of continuance by Euler and irregular singularities by Stokes. And this description as configurations of flags appears in work by Breu and Michel, although they did not have a condition like this, but instead used the Frobenius to relate the last flag and the first flag. And such varieties are called Deligne-Lustig varieties, so this is something very close and relevant for modular representation theory. And the fact that the varieties do not depend on the choice of word, but depend only on an element in the braid group is basically due to is written in Deligne's papers on categorical braid group actions. So in studies of some braid invariants. And in type A, these varieties appeared recently, relatively recently, in works on symplectic geometry. So I wrote the name of Kalman, but I should probably also mention works of Schende, Troyman, Zaslov, Troyman, Williams, Zaslov. Series of works, some with Williams, some without Williams. And one of collaborators, Roger Casals, and his co-authors. Again, Zaslov, Dapingwenk, and others. So there is a description in terms of symplectic geometry, namely the variety is a spectrum of the zeros homology of certain differential graded algebra associated with Legendre enclosure of our braid, whatever it means. I don't think I want to go into details. But there is a symplectic interpretation of these varieties, and symplectic interpretation, in fact, says that basically the varieties up to C factors or C star factors should not depend on the closure on the braid, but only on its closure, up to some half twists involved and some technical details. And also certain vector bundles on over braid varieties can be used in order to stratify vector bundles again for character varieties. And this stratification and further stratification of our braid varieties, which I will discuss a bit more in detail afterwards, has been used by Anton Mellet in his proof of the curious Lefschetz property for character varieties. So these are some appearances in rather different contexts. And one more is the relation to link invariance, which, so I took this slide from a talk where I discussed another properties of braid varieties. What is relevant here is that we have something like this. So what is on the left-hand side and what is on the right-hand side? So we pick some braid word. We complete it by delta, which is a braid lift of W node, half twist. Take corresponding braid variety. It admits a torus section, and one can take its torus equivalent homology together with weight filtration and get some doubly graded homology theory, or doubly graded thing. And what is this thing? It has a different description, which is some part of triply graded Kavanagh-Razansky homology, categorifying some link polynomials of the closure of the same braid. So this is what is written in more detail here, and I would rather skip all the definitions, but there is a categorical description of certain link homology, which are invariants, at least some parts of it are invariants of closures of the braid. And this implies somehow that cohomology of this braid varieties are invariants of this braid closures, or invariants of link. And another paper by part of our collaborators described our braid varieties as somewhat invariant of braid closures. So the paper by Cassels, Eugene, myself, and Cimental. The second one is invariance, concerns with invariance of these varieties. So this paper is currently under revision, so it's not everything is precise there, but the main message is should be correct. Okay. More importantly for us, so-called open Richardson varieties can be realized as this brick variety, guys. And going a bit forward, a bit ahead of myself, I would say that there is a conjecture by Bernard Leclerc, which says that open Richardson varieties, or ring of functions on open Richardson varieties, admit cluster algebra structures. which are particularly nice. So it coincides with upper cluster algebra and admit Rednick sequence, whatever it means. This is served as a motivation to study the cluster structures. One of the motivations to look for cluster structures on all braid varieties, which is the main result, which I will present a bit later. So if we have what is an open Richardson variety, it is parameterized by two permutations. So here I write permutations. This is in type A, but it can be described in all types. So flag variety in type A has strat parameterized by permutations. Flag variety, another type, has strat parameterized by elements of the while group. There are two decompositions. One is the Schubert decomposition, which is similar to Brouillard decomposition that we had before. Another is opposite Schubert decomposition, which uses opposite Borel. And strata are parameterized, as I said, by these guys. And one can take an intersection of open Schubert variety for one while group element and open opposite Schubert variety for another while group element. And this is called an open Richardson variety. So they and their closures appeared and have been studied from the perspective of Kazhdan-Lustig polynomials. Basically, Kazhdan-Lustig polynomials count points of this guy over finite fields. It is non-empty if and only if U is smaller than W or less or equal than W in the Brouillard order. And theorem, which is written in the same paper that I mentioned on the last slide, but goes back to Brion, basically, slightly different terms, says that Richardson varieties can be realized as braid varieties for such words. So this is a minimal braid lift of the larger guy, and this is a minimal braid lift of complement to a smaller guy inside W. So we went from configurations of flags and pieces inside of varieties of configurations of R+1 flags to pieces inside a single flag variety, which is just single flag. So we have G mod B to R+1, and we can take certain projection to G mod B, and side here we have X of this beta of W, beta of U inverse W naught, and it projects to R U W inside this guy, and this projection is an isomorphism. So it's a resolution of singularities studied by Brion and similar to Bot-Samerson resolutions of Schubert varieties. For closed Richardson varieties, which are the same intersection, but for closed Schubert cells. But it's an isomorphism on open strata. And there is a way to go even further in our projections. So we take projection, and one can go one step further, and inside the full flag variety, project those to Grassmannians in type A, and then the image of Richardson variety will be a so-called positroid variety. So Grassmannian admits a stratification by so-called open positroid varieties, which have many different combinatorial descriptions by Poisnikov and by Knudsen, Lammert, mentioned in the previous slide. So one can define them in terms of cycling rank matrices, some juggling, pairs of permutations. So this is description related to Richardson, guys. so-called decorated affine permutations, and some special Plaby graphs, which is due to Postnikov. So there is a, as I said, there is a projection from flex to Grassmannians, and the image of Richardson is always a positroid, and moreover, it's an isomorphism for special pairs of U and W. So there is a condition on W to be K-Grassmannian, whatever it means, and the positroids are isomorphic to open Richardson varieties. So as a corollary, we get that open positroids are also braid varieties. And another example is so-called double Bott-Samuelson varieties studied by Shen and Wang, and also in their paper with Honghao Gao. Slightly different description of slightly different flux incidence problem. So we have again a chain of flux corresponding to letters in beta, but then there is some conditions on these braid matrices that we had before. In principle, slightly different from what we had, but there is an explicit relation. So if we have worth, once again, which starts from a minimal lift of the longest element, or so-called half twist braid, and then add our word beta, then it's the same as this half decorated double Bott-Samuelson guy for beta. So there are many of these varieties, and the fact which was interesting for us is that for this double Bott-Samuelson varieties, Shen and Wang proved the existence of cluster structure, which I will roughly defined on the next slide. And for Richardson varieties, there is this Leclerc conjecture that cluster structure exists. Again, there have been some works toward the proof of this conjecture. I think I did not mention them on the slide, but I will write the names down. So the question is, like, is there a do this all do these things for Bott-Samuelson varieties and Richardson varieties? So since the varieties can now be fit in the same language of braid varieties, can the cluster structure can also be somehow unified? Can we have a natural description for cluster structures on all braid varieties in all types, which contains as a special case this Shen-Wang cluster structures, as a special case conjectured Leclerc cluster structures? And their answer is basically yes, but to proceed to this answer, I will need to say a bit about cluster algebras. So a combinatorial input in the definition of cluster algebra. Okay, so cluster algebra is some subalgebra in a certain ring of Laurent polynomials where Laurent polynomials sign many variables, and it can be described as by some recursive procedure. It can be described by some combinatorial data. I will not give precise definitions, otherwise it would take the other half of the talk. But in principle, you can define it from a quiver in somewhat abstract way. So you have an oriented graph, for example, orientation of your Duncan diagram, but more generally something else. Or in non-simplized types, one would need some skew-symmetrizable matrices. And then there is a notion of cluster seed, which is a quiver, U, and cluster variables, x1, etc., xm. And there is a mutation which changes it to q, well, prime, x1, etc., x I minus 1, xi prime, xi plus 1, etc., xm. This is mu I mutation, which is some rule. which I will not give. Then, how to get the cluster algebra? You start from this abstract thing, x1, xm, some formal variables, and then you change them one by one iteratively. You can change first, then second, then third, then first, then second, then third, etc., etc., etc. You get a bunch of new things. It turns out that, which I also call cluster variables. It turns out they're all Laurent polynomials in initial cluster variables. And then you take an algebra which is generated by all these guys. Some weird thing. You might have a lot of relations. You might have something. I mean, you definitely have some relations, but more like algebraic relations. And there is a so-called upper cluster algebra, which is much easier to understand, to describe. Is intersection of Laurent polynomial rings of all these cluster seeds of all these bunches of variables. So in principle, these are two different subalgebras inside a certain Laurent polynomial ring. Sometimes they coincide. So what does it mean in geometric terms? That was very weird sketch of an algebraic definition. And we say, so there are somewhat different notions of what a cluster variety is, but we say that variety admits a cluster structure if its coordinate ring or ring of function is an upper cluster algebra. So morally, what we will get is that spectrum of x of beta is an upper cluster algebra. U of something, of some quiver, and it's also isomorphic to A on the cluster algebra of the same quiver. Sorry. Sorry. This is not what I wanted to write, of course. I wanted to say that x of beta is isomorphic to spectrum of U of something. And also isomorphic to spectrum of A of something. Or in particular, the coordinate ring is, the ring of function is U and A. But what does the definition mean? It says that there is an atlas, not in precise sense as atlas on open says, but there is something which is, there are a bunch of toric pieces inside our variety, toric charts, which I call cluster charts, one specified initial chart, and transition maps which correspond to mutations. So the charts cover the variety up to dimension 2. Each chart must be equipped with an explicit basis of cluster variables, and the functions extend to regular functions on the entire variety, and transition maps send cluster variables in one chart to another chart by this mutation rule, which I did not describe, but it's some binomial mutation rule. So what we want to get at the end is a bunch of toric charts in a variety, in braid variety, some quiver corresponding to each toric chart, and regular functions which are irreducible elements of ring of functions, and change when we change the toric chart according to this mutation rule. So, well, not the slide is called cohomology, but it's really not only about cohomology, it's about everything. So under certain conditions, existence of cluster structure can say something about algebra, and so something about the variety, which is a spectrum of this algebra. So if the quiver admits something which is called Redonic sequence, certain combinatorial thing, then apparently this results in existence of certain two nice bases in the cluster algebra. So in the ring of function of your variety, if you know that ring of function is cluster algebra for square administrative sequence. So one is called the canonical basis of theta functions. This is, so the first thing is due to Gross, Hacking, Kilkansevich. And another basis, which is due to Chin. And they're parameterized by something that I have not defined. So what is it? We have our variety, which is glued out of torque charts. Now assume that we take dual tori, dual lattices to each chart, and take somewhat dual, in some sense, dual mutation rule, but slightly different mutation rule, and glue these dual torque charts according to these mutation rules. Dual mutation rules. What is defined is so-called cluster X variety. There, cluster variables are only rational functions, not necessarily regular, but so which is kind of bad. But the good thing is that it carries a canonical Poisson structure, which can be used to quantizations of the variety or of ring of functions of original variety as well, compatible with all this cluster structure, and also related to total positivity and whatnot. So if we have a cluster, if we know that our variety admits a cluster structure and cluster structure is particularly nice, then we can say something about basis in our variety in the ring of functions. Also, sometimes under certain conditions, cluster algebra and upper cluster algebra coincide, and then we can use this recursive combinatorics of mutations. And also sometimes when so-called Lewis property is satisfied in particular, we can say something about mixed shot structure. Basically, it satisfies the curious Lefschetz property with respect to some two form compatible with cluster structure. And the last thing is another hint, maybe, towards considering, towards thinking that braid varieties may admit cluster structures. It is a very naive thought, but it worked in the end. Is that there is this two form that I mentioned, defined by Anton Mellet to prove curious Lefschetz properties for braid varieties and for character varieties. And I don't think it made the slides, but in the cluster structure we construct, the two form defining the quiver is the same up to some rescaling by scalars as this form defined by Mellet in terms of Maurer-Cartan groups of Maurer-Cartan forms on the group G. So what are finally the main results? So here are main results. I will say a few comments about some parallel works after I see the results. So assume that we have a simple algebraic group. Almost everything is done for all types. There is one small combinatorial check for G2, which is, I mean, in some sense it's small, but it involves like 100 or so of small checks, and we haven't done this yet because we're a bit lazy. But for anything, for any group not of type G2, and for any positive braid or braid which admits a positive braid word, we can define our variety, and then the ring of regular functions or coordinate ring is both an upper cluster algebra and the cluster algebra. And there is some thing which I will define in a moment, so-called de-measure width, which gives us a cluster seed. So what does it mean? We have something which is called de-measure width, whatever it is. It defines us. So this means that we have a quiver Q and parameterization. Parameterization is this isomorphism. So we can define a quiver with formal variables x1, etc., xm corresponding to vertices of a quiver. And well, something more precise should be set in skew-symmetrizable case in non-simply laced types. But say in simply laced types, we have a quiver. We have a formally defined cluster algebra, upper cluster algebra. And now what I say is that we can find also a specific regular functions in the variety such that identification of x1, etc., xm with these regular functions for certain width gives an isomorphism. And in some sense, the initial cluster chart is sent to some nice cluster chart. And there are other widths, which I will define in a moment, which give other quivers. And we have access to many, many cluster charts in this cluster algebra. We have nice combinatorial descriptions, and we have some geometric interpretation of these guys. There is a hope that there is a relation to symplectic geometry. And all these quivers come with parameterizations of varieties, of ring of functions of varieties. So we prove that we have cluster structure on a variety, and since it submits a reddening sequence, again, this is something that I have not defined but used. All these things about basis, existence of basis, are also satisfied. So this ring of functions admits canonical basis of theta functions and generic basis, both parameterized by tropical points of dual X varieties. And in fact, in simply laced types, the same variety is this dual X cluster X variety. In non-simply laced types, one has to take the same braid word, but for length dual grid. So you take the same variety, and it can be glued. It can be thought of being glued out of tori and out of dual tori, and we have some regular functions which gives cluster structure, and we have some rational functions which give a cluster structure of cluster X variety. And there are a bunch of duality conjectures, so due to Fock and Goncharov. Which hold for these pairs of varieties. And one thing that follows is conjecture by Bernard Leclerc that I mentioned orally, is that for simply laced groups, open Richardson varieties admit a cluster structure. And there was a difficulty with Leclerc conjecture, is that it was formulated in terms of categorifications of cluster algebras, whatever it means. So there is he proved that there exists some categorical thing which defines a certain cluster algebra, certain quiver. And there is a cluster algebra which is a sub-algebra of coordinate ring of Richardson variety. But there are many issues, like, is it entire sub-algebra, entire ring of functions? Do we have A equal to U? And these are somewhat resolvable. So recently, Chow and Keller announced that they have a proof that U equals coordinate ring of Richardson. And my understanding is that the paper should appear again in upcoming weeks. There are some works by Menard who gave a priori different quiver, probably the same, not explicitly, but algorithmically. And yeah, I did not say that, but Leclerc gave this categorical thing, but he could not describe a quiver, except for some small cases. Because so if you understand what I say, it's good. So this is for expert. We have cluster tilting object in the category of representations of pre-projective algebra. Then you have certain torsion subcategory which corresponds to W. You take a cluster tilting object there, which can be described very explicitly. But then you have inside this torsion subcategory another torsion pair, or more precise, there is an intersection of this torsion subcategory with torsion pair inside entire model category of projective algebra. And you know that I think torsion-free part, maybe torsion part of cluster tilting object for W should be cluster tilting for the category which corresponds to the pair of V and W. But describing explicitly this torsion-free or torsion part, or its basic summand, maximal basic summand, is complicated. It's so it's not obvious at all how to do this. Like, you know that there is, if you have a torsion pair, there exists certain short exact sequence, which is in general not split. And you need to take the first or the last, depending on the choice of Borel, term of the short exact sequence. Then you need to take all its indecomposable summands, one copy of them, and remove the rest. And you want to draw a quiver of endomorphism algebra of this guy. But if you don't know the short exact sequence explicitly, then you are screwed, basically. How would you do that? You know that it exists, but you don't have an explicit description. Then you also need to take some indecomposable summands, blah, blah, blah. This is very, very non-explicit. Then there is an algorithm by Menard which gives explicit procedure of how to get from cluster tilting object for W to this, to some cluster tilting objects for pair of V and W. So you can plug in, you can compute. Again, it's maybe not precisely super explicit, but it's a progress. And there is another construction in type A by Ingermanson, which is also not super explicit, but again, there is some combinatorial rule. If you know how to count some paths in the varying diagram, in the diagram of your braid word, basically, then you have some description, but it is a bit complicated. So one thing that I wanted to emphasize is that we have very explicit description of a quiver for rich Demazur with whatever it means. This I will have time to define. And for some Demazur waves, we have very explicit description of cluster variables. For others, this are again somewhat implicit, but we know that one is enough. It is we have an initial cluster seed. And before I go further, I need to say that there is a parallel work by Galashan, Lam, Sherman Bennett, and Speyer. So it also should appear at some point. Thomas Lam gave a talk at the seminar that Hasse and I organized, and there are notes available and records if you're interested. So my understanding is that currently they have proof in type A, work in progress in other types, of this result. They do not discuss X structure or any extra information that we discussed. And they have a priori different cluster structure, probably they are closely related to each other. Maybe they coincide. Nobody has checked that yet. So this is a task for combinatorial, for people interested in combinatorics. Maybe some combinations of authors of our paper and their paper will work this out. Maybe not. How do we get toric charts? So very quickly, if we remove a letter in our braid, then we have the following map. We have an isomorphism of some piece of a variety associated with a longer word. Delta beta can be removed here. It's slightly different notation. And C star times variety for smaller word. So one can check that quite often. So if variety was of this form, beta delta or delta beta, then for each choice of removing crossings of beta from this guy or letters of beta, there exists an open set inside the big variety, which is isomorphic to a torus. So it is a toric chart. So this is slide is a bit clumsy, but what is the main message is that if you have a variety of the word of the form beta delta or maybe delta beta, then all letters here picked in some order. So ordering of these guys gives a toric chart in the variety for x of beta delta or delta beta. There are some of them give you the same chart, some of them are different. It depends. So the theorem that I mentioned before says that, so this is an older notation, says that if we take this half decorated double Bose Samuelson cells that I mentioned before, then they admit cluster structures, and these orders removing of crossings from the part which is beta complement to delta on the left, on the right, depending on the word, cover everything up to codimension 2. And these are toric charts which gives the cluster structure. So what we do in this paper that I'm presenting is that we can now study words which do not contain delta at the end or at the beginning, and we have more cluster charts. We have strata which describes not only by removing letters in some order, but also like removing letters in some order and performing braid moves, basically. So what are these weaves? So it is a planar graph which is with edges labeled by braid generators, so simple reflections, and vertices which are of types. So this corresponds to braid move or braid relation. This is braid move. And this is something which is sigma I goes to sigma I. So if you want to think of dual picture, maybe some people think about triangulations of polygons or something by describing all these combinatorics, then building blocks of the dual picture are hexagons with labeled edges, squares with labeled edges, and triangles. Triangles have edges I. And in the quiver, which we construct, which I will not have time to properly define, there is a vertex inside each triangle, and there is some bookkeeping involving hexagons and squares, and similar to, quite surprisingly, to a story about Mirkovich-Villain cycles, which gives you exchange matrix, or which gives you adjacency matrix of a quiver. So yeah, let me give examples of weaves. So what are weaves? Weaves can be thought of paths from top, this is beta, to bottom, which in this case is the measure of beta, which is the longest element in S3. Here we did not continue to the bottom, but we can, and it's a binary tree. So weaves in braid on 2 strands with 1 generator are nothing but, so weaves from beta to delta of beta, which is always S1 or sigma 1 if you think in terms of braids, are just rooted binary trees. And more generally, you can have pictures like this, pictures like on this slide. So if you think of this blue edges corresponding to generator S1 and red edges to generator S2, then you have 1 to 1 at the bottom, and you have 1 1 2 2 1 1 2 2 at the top. So each weave can be thought of written as in a rectangle R, and you have flags such that the leftmost is a standard flag, the rightmost is, well, B minus if you have W naught at the bottom, in general something which differs by the measure. And the fact is that if you fix flags here, and you say that each edge gives you relative positions of 2 neighbors, then you can determine all the rest. And what we have in our variety originally is kind of just the word at the top. So we have, I don't have time to write in colors properly, but we have something like this. We have 1 1 2 2 1 1, sorry, 2 2. You have 1 2 1, and then you can have many ways to go from top to bottom by moves of this form. Each such way is called a divisor wave. And each such thing defines your cluster chart. So first of all, it defines a quiver. I will skip through to a quiver. Maybe we'll take a quiver like this. So the vertices of the quiver correspond to pieces of this diagrammatic thing of a wave. So pieces of the path from beta to, say, W naught, which start from, I don't know, trivalent vertex and go somewhere to the bottom, satisfying certain rules, which I don't describe on the slides. And yeah, this won't tell you much. But you need to know what happens when you cross 6-valent vertex, what happens when you cross trivalent vertex, etc. So you have a bunch of pieces in this picture. Each of them corresponds to vertex in the quiver, and there are some rules involving, again, the combinatorics of a diagram, which gives you what are the arrows in this quiver. So here is a picture without the quiver. Again, so you start from trivalent and you go to the bottom, but sometimes you have to bifurcate, sometimes you don't. There is somewhat complicated rule, but in fact, it's easier to describe than what one could have thought. And it involves changes of some tropical versions of Lustig factorization coordinates, which appeared in works of Bernstein, Fomin, and Zelevinsky preceding the definition of cluster algebras, and also appear in the context of Mirkovich, Whelan, and polytopes, and already an original work by Kamnitzer. So maybe last comment. I think I started a few minutes late, so I use 2 more minutes if it's fine with you.
Yeah, go ahead.
Okay, so we have a bunch of these diagrams, and it's very similar to circle calculus, which is not surprising since I mentioned that there is a relation to Rouquier complexes, and circle calculus concerns morphisms between Bose-Emerson bimodals, somewhat of a similar nature, although one can think of our guys as so-called open circle calculus. The crucial difference is that there is an associativity relation, which says that in circle calculus, they have the same picture, but it says that there is an associativity between morphisms of Bose-Emersons. But when one thinks about Rouquier complexes, well, somehow one should not think of associative algebra. One should think of maybe infinity stuff hidden somewhere, but on the level of clusters things, this corresponds to mutation. So this is precisely the cluster mutation. This is precisely where things change. So here you have, for example, this vertex, and it corresponds to this piece of the diagram. And we have this piece of the diagram, hopefully it's readable. And it gets replaced to this. And one can check that it's this hopefully I don't mess the orientation, but it's not very important. I think the rule is like this. Maybe it's the opposite. So this is a mutation between 2 quivers of type A1 with 1 frozen vertex. And more generally, here you have A2 quiver, which corresponds to widths from sigma 1 to the 4 to sigma, or S to the 4th if S is a unique generator to S. So you have 5 mutation equivalent, but not just equivalent widths. You have 5 torque charts, and these are clusters. They correspond to clusters in the cluster algebra of type A2. And there is another description of the same variety up to C star factors, which involves words on 3 strands, and you go from this guy to its de-Mazur product, which is longest element in S3. So each thing here corresponds to a width. So each edge is vertex like this, or vertex like this, etc. So each pass from top to bottom corresponds to de-Mazur width, and there are mutations, and one can check that the graph of mutation graph after you quotient out by equivalence is again a pentagon, which is not a surprise because both of these guys correspond to big positroid cell in Grassmannian 2.5. Up to some torus factors, there is a description like this, which says that, well, it's Grassmannian 2.5, and this description thinks about the same variety in Grassmannian 3.5, which is the same variety. And the varieties are isomorphic. One can think in terms of positroids, one can think about in terms of these links, which are braid closures. Both are cluster types A2. It's over recover of all clusters via our WIF calculus. And this is somewhat different to many construction involving Richardson varieties, in the sense that usually if you have a word, you have one cluster chart for a word and not one cluster chart, say, for order of letter, for different orderings of letters in the same word. So if one thinks only of word sigma 1 to some power, you can recover only one cluster chart in some descriptions. For example, Leclerc description or Menard description, but you can recover all 5 using this. I should stop. Thanks a lot for your attention.